We are now looking at chapter 10, which is application of differentiation. So as always, I'll start with a little bit about story of differentiation and the application. So we looked at the differentiation, which could be also called as sensitivity, like how sensitive you are when you make a change in the dependent variable. Dependent variable is something that drives everything. So in life, if money is everything, then money is a dependent variable that drives everything. Money is a variable that drives demand. Money is a variable that drives supply. So your sensitivity with money. So sensitivity is one way to look at that. The other way is slope, which is rate of change, or in general change, how things are changing. Are they changing fast? Are they changing slow? And we also use the term derivative, the first derivative, because we want to find out how things are changing or how the values are derived. We talked about the applications in physics, the oldest application being playing around with how time an object would take to come down. So if we throw something up in the air, the acceleration would cause the speed to come down. At some point of time, the speed would be zero, and then it would start coming back to Earth. So this is an application of finding out the maximum point, that when the speed is zero, that would be the maximum point. So when the second if you want to find out that place, so we'll first take a differential, put it zero, and we'll take another differential if gravity was acting in the opposite direction, which means that if the second differential was negative, then it's the highest point. But there are other charts that we would also look at. We generally see the equation of a straight line, because this is something that's very easy to understand, and the differentiation of this line is how much this line is tilted. So if it's more tilted, uh, it means that it's more sensitive, or if you change a small thing in x, then a greater change would happen in y. We had a derivation of this. Y, the differentiation of x square is 2x, and when we put x plus dx and expand it and plug in the values, we saw that the rate of change is 2x. In other words, if you are on this line x square, on this curve x square, and you go 100 units on the right on the x-axis, and you want to find out at how much distance you have to move up when you move a small distance x, then it's like 2 times how far you are. So we'll look at a chart as well. So we'll have increasing or decreasing a function that might be increasing or decreasing, which means that as you increase x, its value must be increasing or decreasing. We'll look at that. We'll look at convex and concave shapes. The first thing which comes into my mind is the concave and convex lenses that we have in the eyes. So some people have trouble in seeing far off objects, some people have trouble seeing the close one. So we have different types of lenses, and the shape is like bulging in and bulging out, and those are the things in which I can probably relate. So throwing a ball in the sky is most intuitive. So there is a thing that if you have to differentiate and put the first derivative equal to 0, because you want to put the speed equal to 0. Speed is the first derivative of distance, and you take a second derivative, and if it's negative, which means that if the acceleration is negative, which means that you are throwing it up and not down, then that is the highest point. So that's one way to remember the story. Now charts have their own story, which we'll look at the charts given in the book. We should also be able to draw the graph of x cube or x to the power 5 or x to the power 4, because all of these graphs have something common, and we'll look at the maximum and the minimum point of these graphs. Some places where we might see this is elasticity or maximizing the output, finding out the maximum part, and we'll also use Wolfram website. Now we'll look at the book and see the graphs and try to understand this part, like the maxima, minima, and things like that.